Good morning, everyone. Thanks very much for coming in such early morning. It's really good to see that the crowd here. So my name is Bing He. I'm moderating this session, and we're going to have 3 speakers today. I apologize. The fourth speaker, Dr. Karl from Harvard Medical School, was not able to get a visa in time to come to Geneva. Therefore, we will have 3 speakers, and the first speaker is Dr. Karl Friston. Karl really doesn't need any introduction, and every one of you know from his SPM, DCM, pioneering seminal work, and also not mention the very recent Glass Brain Award just given a couple days ago. Karl, please.
Thank you very much. Good. It's a great pleasure. Well, I always say it's a great pleasure to be here. In a general sense, it is. At the moment, I've got a hangover, so it's not. I can't quite access that pleasure. However, let's proceed. My talk is going to follow on, I think, from the theme or the idea Fernando Lopes da Silva ended on yesterday. So I'm going to try and answer the question directly. Functional connectivity or causality in the brain, how do we know? And the answer that I'm going to offer is that if we start off with a model that is causal, and then we fit that model to empirical data, then by definition we know that our inference is about a causal architecture. So summarized here, we can know, in one sense, if we invert a causal model of functional connectivity. However, there's one small problem, and that problem is an inverse problem. It's the sort of problem we contend with every day. It's ill-posed. So that's the answer I'm going to offer. I'm going to spend the next 20 minutes just taking you through the structure, the substance of that problem, and some solutions that we have devised using dynamic causal modeling. So the basic idea here is that we're going to use functional connectivity as the data. So functional connectivity will summarize our observations, the consequences of brain activity generating signals that are measured. And we're going to treat effective connectivity as the cause, the hidden or the latent causes of the functional connectivity that has been measured. And we're going to do a Bayesian model inversion mapping from the functional connectivity to get at the effective connectivity. So to unpack that perspective on the answer, we need to establish the difference between functional, effective, and in fact anatomical connectivity. So I'm going to use slides from my friend Hae-Jong Park in an article we wrote several years ago now. So he did some beautiful graphics, and what I want to highlight here is the conceptual distinction between structural and anatomical connectivity, which I'm not going to talk about, functional connectivity and effective connectivity. And very simply, functional connectivity is a statement about the statistical dependence between 2 measured time signals. And we assume that that dependency is caused by causal coupling or directed effective connectivity between the neural systems generating the signals. It's a very important distinction, particularly from the point of view of what we're going to be talking about. The problem, the small problem, in fact a very big problem, is that going from the functional connectivity to the effective connectivity is an ill-posed problem, in the sense that there are a universe of different effective connections or architectures that could generate the same data or functional connectivity. And Hae-Jong illustrated that here just by simulating a little toy example, showing that very, very different patterns of coupling strengths, effective connectivity, can generate correlation patterns that look very, very similar. So the challenge ahead of us then is how to get from these observations and solve this ill-posed problem to infer the underlying architectures of interest. So I'm going to use this graphic throughout the rest of the talk. What is shown here is the stream or the way that the data are actually generated. And we assume that right in the top panel here, we assume that there are some either endogenous fluctuations in the brain or designed experimental inputs that cause neural activity, and that neural activity is distributed. It responds in some structured way according to a model, and that model is the equation at the top of the slide there. The x dot is equal to a function of the activity x and these fluctuations that are driving the system. And finally, theta, these are the parameters of interest. And they're going to encode the effective connectivity adjacency matrix, and I'm cartooned that with the matrix on the side there. And then these recurrent dynamical interactions among different brain regions generate signal, Y, that is burdened with a little bit of observation noise. And then we can summarize those data very compactly, very efficiently in terms of, say, a covariance or correlation matrix or autocovariance function. And I'm calling that sigma down at the bottom there. So from the perspective of mapping from causes U to consequences sigma or Y, that's the way that the data are generated. That's our forward model. So from effective connectivity to functional connectivity. And the solution or the problem is how do we get back, or how do we do the inverse mapping from functional connectivity to effective connectivity? And I'm not going to go into the detail about the procedures, but the procedures that I will illustrate are based upon Bayesian model inversion, going backwards. And that usually can be expressed as an optimization problem, optimizing the free energy of the data and expectations or beliefs about the underlying causes, namely the effective connectivity. Crucially, what that gives us are two things. First of all, optimizing some probability distribution over the unknown connection strengths gives us a posterior distribution about the best explanation for the data, but it also gives us the probability of those data under that sort of model. That's called the model evidence. That's going to be a very important thing in terms of disambiguating between different explanations for the data. So let me just graphically illustrate for you what I meant by the ill-posed problem. Remember before I said that there are going to be a universe of different explanations for one functional connectivity observation. What that model evidence does, it gives you a way of scoring the goodness of all these alternative explanations. So here I've got, say, about 8 explanations. For each one of those, I can optimize the parameters, derive the log evidence, and then look at the profile of evidences and select the one that has the greatest evidence. And I can work out the probability of that model given my functional connectivity. And that's cartooned on the right-hand side there. If we have a score or a measure of belief at each of these models, we can then go back and weight each of the different estimated effective connectivities in proportion to the evidence for the model from which that pattern of effective connection strengths came from. That's known as Bayesian model averaging. It's a very useful device that acknowledges or absorbs ignorance about the particular model or architecture at generating the data. I just want to emphasize the importance of the model evidence or Bayesian model evidence and its structure. It can always be written in 2 bits. It has an accuracy term, which just reflects the goodness of fit, and then a complexity term. So the evidence here, summarized in terms of a free energy, is the difference between the accuracy and the complexity. So the complexity is the number of parameters you're using to provide an accurate explanation. It's the degree to which your beliefs about the parameters, the effective connectivity, depart from those prior beliefs in order to give a good explanation. And I think it's important to realize that the evidence is a function of the data. So there is no true model, there is no best model, but there's always a best model for a particular data set at hand. So I've tried to illustrate that at the bottom here, that if you can think of a range or a space of different models with different complexities, say a very simple fMRI model using a bilinear approximation there on the left-hand side, right through to the very complicated neural mass models that Professor Lopez da Silva was talking about yesterday. For different data, there will be a different optimum degree of complexity, and that optimum will maximize the Bayesian model evidence that you can actually measure, you can actually score and determine what is the best level of complexity for any given data. To do that, obviously, you need to score the evidence for all sorts of different models. That can be computationally very demanding. There are lots of interesting developments recently based upon Bayesian model reduction. Effectively, what this does is it means that you can evaluate the evidence for a model if you reduced it by removing certain parameters, by pruning certain parameters, without having to refit the model. It's closely related to earlier approaches or special cases like the Savage-Dickey ratio. The image is the best I could do when I Googled Bayesian model reduction. It's actually a reduced model, I think sporting a thong and a tango. Here's an example of it in action, an empirical example. This is our classic teaching data set, fMRI study of attention to motion, where we had a handful of regions, but just having a handful of regions induces n-squared connections, and then you have thousands, hundreds and thousands of permutations of all which connections can be on or off. And in this example, we scored within a few minutes over, I think, 10,000 models. And I've just plotted there in the graph on the upper right the evidence for all those models, and then the lower one, the posterior probability, enabling us to identify and then do Bayesian model averaging to identify the underlying architecture, and then we could then go on and make comments or interpret it, or indeed do graph theoretic analyses on that effective connectivity. But what I'm going to do now is very briefly close by just surveying the different ways in which we can organize those data and perform that Bayesian model inversion. So let's go back to our generative forward model of the data and just focus not on the functional connectivity, but actually on the time series itself. And if we now parameterize those fluctuations in terms of, say, some constrained temporal basis set, then we can use that model and the observed data to maximize the Bayesian model evidence and to do the model inversion, and thereby create estimators of the effective connectivity. And that approach has actually been used by Bharat Biswal, using this idea of parameterizing unknown drives to the neural system, generating the actual time series themselves. People who are interested in functional connectivity will be more interested in modeling and generating the functional connectivity either in time or in frequency space. We'll come to that in a second. There is another development which enables one not to use deterministic models of the fluctuations, but to accept that they are stochastic and endogenous, certainly in resting state fMRI. It's a very useful assumption. And that leads us to stochastic DCM. So here we're not just estimating the parameters, we're also estimating the states. Computation is very expensive, but sometimes quite useful if you actually want to estimate the neuronal activity generating your time series. In terms of spectral DCM, well, let's go back to our functional connectivity matrix. That's a nice summary of the second-order behavior of the data. And in fact, in terms of generating the second-order behavior, the correlation structure in the data, we only need to consider the second-order correlation structure, the way the data were caused, namely the autocorrelation function of those endogenous fluctuations. We can do that in time, or we can do it in frequency, mathematically identical. So if we know the power laws or the spectral form of endogenous fluctuations, then we can work out what we would have seen if we had this particular adjacency matrix or effective connectivity in play, and therefore we have a forward model, and therefore we can invert it in principle and optimize the parameters of that model. And Adil Razi here has used this to great effect in doing simulations, looking at the efficiency of resting state fMRI and identifying effective connectivity using that approach. So finally, I'm going to try and, as promised in this brief abstract here, just close the gap between, or highlight formally, the points of contact between functional and effective connectivity beyond this notion that effective connectivity causes functional connectivity. And the particular point of contact arises in this special case. If we imagine that the effective directed connections amongst all areas were equal and identical, so they're complete reciprocal. So the connection from A to B was the same as from B to A. A very special and pleasing case arises from this general Ford model. And that case essentially allows us to express the functional connectivity almost directly in terms of the effective connectivity. The expression, I won't take you through the equations, but if we make one more simplifying assumption that there is no observation noise, then it turns out that under this generative model with symmetric connectivity that can be decomposed into eigenmodes or brane modes or principal components and their eigenvalues, which I've cartooned as a red diagonal in the middle of those three matrices there, it means we only have to estimate the eigenvalues. And furthermore, if we assume there is no observation noise, then we have this special case where the effective connectivity becomes a negative inverse of the functional connectivity. Of course, a lot of you will recognize that as the partial correlation. It's just so the partial correlation, the inverse of the negative functional connectivity, is exactly the effective connectivity if there was no observation noise and if all the coupling was exactly symmetric. And that rests, well, one can show that easily using that eigendecomposition cartooned on the upper right. Of course, we don't necessarily want to make that strong assumption about reciprocal connectivity. However, we can still use the same decomposition in this eigenspace to consider patterns or modes of activity and relax the asymmetry assumption. Now you'll see that the eigenvalues, that leading diagonal of red little squares, has now filled in. And that filling in is a reflection of the fact that we've now relaxed the symmetry constraints. But we're still keeping the notion of intrinsic brane modes, eigenmodes, in terms of summarizing the overall behavior of this system. And if we do that, the nice thing is we can throw away those eigenmodes that contribute a trivial amount to the functional connectivity, and then we can start then to invert a full either spectral, stochastic, or deterministic DCM using very large numbers of nodes, because we've finessed the computational problems of inverting large DCMs. And this is an example from Mohammed, who's looked at the language system and just scored the number of modes that you would need to maximize the model evidence. So the number of modes in and of itself becomes a model parameter, and we can optimize that in the usual way by maximizing model evidence. So I will leave you with a nice quote from Feynman that's pertinent, I think, to the questions about coupling and connectivity. Nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. Isn't that lovely? Thank you very much.
Thank you very much, Karl. And we have time for question. Sorry. And we do have the microphone around, and please use a mic for the question. Okay.
I just make a comment at on your very last comment, in which you've reminded people that the inverse of the covariance matrix, when suitably scaled, gives you the partial correlations. And I'm very glad you said that. I think a lot of people don't really quite get that. I just wanted to draw attention to a frequency domain extension of that result. So there's a beautiful formula. If you have a multivariate autoregressive process, there's a beautiful formula which shows that the inverse of that multivariate spectrum gives you conditional coherences. Mm-hmm. So it's exactly the frequency domain extension of that result that you just quoted.
Mm-hmm. Thank you.
Yes, please.
Thanks. We heard 2 days ago about the different modes consisting of controlled processes taking control of saliency networks and of top-up stimuli in the limbic system. Is your notion of mode similar or related to that or not?
Yeah, no, absolutely, yeah. So the mode is just a pattern of activity so changing the amplitude of the mode generates a particular sort of pattern or contribution to the data, and then if you mix a number of modes together, you have a good summary of the overall distributed activity. So things like ICA and principal component analysis that were the genesis of the notion of intrinsic brain networks, or like the default mode or the Sorensen mode, or they are predicated on a decomposition of a somewhat complicated pattern of functional connectivity into a linear mixture of these modes. And mathematically, I'm calling those eigenmodes because that principal component analysis rests upon an eigen decomposition. So it's exactly the same thing, yes.
Karl, if I may ask one question, the DCM model has been very widely used in functional MRI data. And there's recently for quite a bit of time, interested to use that to model the EEG, MEG, electrophysiological activity. Can you comment on that when we applying DCM model? Is there anything that the user should pay attention in terms of difference between modeling the fMRI data versus electrophysiology data, or probably it's just the same? I thought, just want to bring this question up.
No, thank you. Yeah, there are, from my point of view, very exciting developments that again, Fernando spoke to yesterday about using neural mass models to get into the nitty-gritty, into the synaptic architectures, right down at the level of canonical microcircuits and sort of inter- and intralaminar message passing. To do that, you have to construct dynamic causal models that have that granularity, that can contain those sorts of questions about at the level of synaptic efficacy. So we have to move away from the very simple, usually bilinear approximations that are used for fMRI to much more biophysically grounded models. And we've borrowed from the history of neural mass modeling off the shelf, essentially, and have used those. What should the user know? Well, as intimated in that sort of graphic showing differences in complexity, the repertoire of models that you can put to EEG, MEG, LFP data greater. They are much more nonlinear. They have many more moving parts. So it makes the specification of the model space and the scoring or the searching of that model space much more challenging thing. So to be honest, at the moment, DCM for EEG and MEG is something of a power user thing. Whereas the DCM for fMRI, I think, is sufficiently robust and interpretable that you don't really need to worry too much about what's under the hood. You can just go in there, ask your questions.
Okay. If no other question, it's just about the time. Let's thank Karl one more time. Okay, so I will give the next presentation, and if I could have my slide, please. Oops. Shall we talk about the mapping brain electrophysiological connectome? I know that usually we talk about connectome, we refer to structural connectome or maybe fMRI-based connectome. So my presentation has three portions, and one is I wish to present a body of the work that my collaborators and I have been pursuing in the past 10 years or so on integrating electrophysiological source imaging together with the granular causality to achieve the electrophysiological connectome. The second is to address a question that is the title of this symposium, that is, how do we know that we have functional connectivity or causality inside our brain if our access to is non-invasive data? And then the last I want to share a few comments of observation on this topic. So this slide illustrates just as when we talk about their brain connectivity, we have structural connectivity and on the left-hand side of this left side of this picture, and the functional connectivity on the right side. The functional connectivity mainly has been dealt with from functional MRI or electrophysiological data. And one of the points I wish to point out, and which probably has been well and observed, that is our brain activity, including the both functional and effective connectivity, actually is a dynamic process. As this slide, you can see that ultimately the neuronal process is driving this entire information processing process is really this action potential, which is very fast in time. And of course, it's distributed over the three-dimensional space. Just to give one example, this is one of the work that we have been using this electrophysiological information to look into binocular rivalry, and the mechanism is when you are presenting in red or green color to one of the two eyes, and at any given time, and the subject actually perceives either seeing red or seeing green. It does not see the both color at one time. And by integrating with the source imaging and the signal processing, we were able to actually derive the brain response to this dynamic and active process. So this slide just summarizes these functional and or structural imaging and activities, and which is not new, so I'm not going to spend too much time. But I want to bring your attention again to this right lower panel that is showing that while the both functional MRI has served a great and a deal to find out the spatial information, it is relatively speaking and fairly slow. So does not reflecting the brain dynamics in that temporal scale and per se. So this is one of the resting state functional MRI connectivity map, which has been well studied by many groups. As shown here, you can see it's very beautifully and review or delineate what is the brain spatial organizations, but at the same time, one of the things which is a very simple analysis of the signal on the left side of this panel, that is one is electrophysiological signal, the ERP, another is event-related bold signal. And then you look at the spectrum distribution, which is distributed display over the right side, and you can see that the blue color, which illustrates bold fMRI signal, has a very low frequency oscillation, and which is we have one brain, but on one side you can see the high frequency oscillation, as you can observe from electrophysiology, and but you do not see that in time or in spectrum from the bold signal. But if you look at the spatial and the bold signal, it's a very high spatial resolution. So with all these discussion, and one of the approach which we have been pursuing and in collaborating with a number of the research labs is something we call Connectome. Is that we started with EEG or MEG, the electrophysiologic signal generated by the neuronal excitation through volume conduction, and we solved the inverse source imaging problem to find out what is the source distribution inside the brain and the network, and furthermore we estimate the directed connectivity of this network from entirely non-invasive electrophysiological information. So to talk about this, there's one important component, that is the source imaging component. You start from EEG or MEG, and you take advantage of the MRI, essentially T1-weighted MRI anatomic information, serving as a prior to solve this inverse problem to find out source information. Then after that, and one is certainly we're looking into the brain functional networks because it's not evenly distributed, and this go back to this Granger causality notion as early as the 1960s. And Granger, and while studying in the economics, and proposed this bivariate and autoregressive model to saying that if you have two series X and Y, and if the inclusion of the past information of the Y is going to help predicting the future of information of the X, then we say that Y is Granger course X, which has found a tremendous amount of application. And one of the important developments along this line is in 1991, Kaminsky and Blanovarska and extended Granger's and the Granger causality concept or framework to multivariate and autoregressive model, and doing the spectral transformation to frequency domain, then derive their directed transfer function, or something we call DTF. And from this DTF, then you could study a multiple and a channel, and at once look at the directed the functional connectivity, or in the sense of the directed connectivity of any pair of these two nodes. So here, one of the question is then we come to that, how could you can certainly from array of recording, you can always calculate the DTF or Granger causality. Now the question is, how do we know such kind of calculated DTF or Granger causality measure reflect the undergoing the brain functional connectivity or effective connectivity? So this is one of the experimental validation work that we have done. On one hand, we try to apply the Granger causality to study the epileptic network. On the other hand, we utilize epileptic network. In that case, we do know specifically where is the seizure driving force, and in a particular patient, as defined by non-electrophysiological information, or at least not from the scalp. So in this particular case, you can see on the left side of this panel, which shows that this is analysis of ECOG data over the brain surface directly by analyzing interictal spikes. On the left side is clinically defined seizure onset zone, and on the right side of the left panel of this slide showing the Granger causality analysis and derives the outflow region, which coincide with this clinically defined seizure onset zone reasonably well. On the right side of this slide illustrates Granger causality analysis during the ictal, the seizure data. And then once again, the area and showing, and on the left top panel is a clinically defined seizure onset zone, while the other three panels are showing the outflow derived from the ictal analysis of Granger causality. So from here, I really want to bring to your attention and one of the work which is propose this electrophysiological connectome, or integrating the source imaging with the Granger causality analysis, and it was published in 2005. And in this particular approach, you can see that we transform the scalp EEG data, which is shown on the left panel here, and to the cortex at a predefined region of interest. And then once you get that information, and the Granger causality analysis can be performed, so on the left side you can see the DTF value, or the information flow from this source transformed information can be obtained. On the right side of this panel is the outflow or inflow, just showing a regional this information and processing, and as derived from entirely and the non-invasive information. Now, come to here that a question really is, can we trust such kind of totally non-invasive and functional connectivity, or even causality estimation and the result? How could we know? And one of the philosophy we have taken is to perform experimental validation, and in particular we use epileptic network as a testing bed, and certainly not to mention there's a direct clinic application. So this work was conducted 9 years ago. In this case, we applied first time, and from the source image and from the EEG, we image the source information as shown on the left panel. You can see in this particular patient, there are 3 possible regions of seizure and generating and areas. And then after transformed to the source signal, and the Granger causality analysis was performed, and using the DTF and the algorithm, and the arrow in the middle show that what is the information flow. And by doing the statistical testing, significance testing, it was found that in this case, the area shown by the red dot and the area shown by the blue dot actually are driving others, but not particularly this area shown by the green dot, which suggests a possible notion of the primary seizure source versus this secondary and the source due to the propagation in the epileptic network. So in this work, we in total look at 20 seizures in 5 epileptic patients, and their source-based granular causality analysis was able to localize the seizure source in all 20 seizures as defined by the clinical finding. In this particular case is based on MRI and SPECT. We furthermore and looking into another group of the patient, and once again the notion is the same, that by perform the EEG source imaging, you can find out the possible and the seizure source, and from there by doing the granular causality to see that if there's information flow or if there is a causality, and we define that in this particular case, you can see that S1 as shown, it does have and the causality or the directed info and impact to the S2, and which is coincide with and the clinical finding. In this particular case, the patient was resected on the area covered by S1 and became seizure-free. And in total, 10 patients was started, and the majority of them actually within 1 centimeter, their granular causality in combination with EEG source imaging was able to find out the primary seizure source. And in some and the minority, and the error is within 2 centimeter, and only one particular seizure in one patient, which is patient 6, which is found that within 2.5 centimeter. Not just from EEG, we also conducted work by looking at MEG and the signal. In this particular case, you can see that from the 148 channel MEG recordings during interictal spike, and the 3 possible seizure sources was identified after granular causality analysis, and the region which is shown from the D, that there's information flow, that outflow coming out, actually very well coincident with the clinically resected zone in this particular patient, and patient became seizure-free. That suggests that by using this clinically known information that's not entirely based on non-invasive EEG or MEG information, actually we are able to quantify or assess that the validity and effectiveness of such kind of non-invasive imaging and the result. And here is showing another example, not just from EEG or MEG. In this case, actually, we did the simultaneous EEG and MEG recording. So from both EEG and MEG, there were 2 regional possible seizure sources were identified by performing granular causality. And it is quite clear that one of these regions, as shown, driving the other region, and is a seizure source. And as a patient received surgical resection and became seizure-free of that particular area. So, come to here, there's a lot of method to evaluation, certainly, and we could do the computer simulation. Our group has done computer simulation as well. But what is probably more important is experimental validation, because computer simulation is really depending on what kind of model, what's input you put into your simulation. In this case, I would like to bring to your attention to another possible use of granular causality. In this particular patient, we do get intracranial EEG recording, ECOG data in this patient. And then by doing the independent component analysis of the scalp high-density EEG, we found that in total there are 6 independent components which are possible seizure source. And then actually we performed the granular causality analysis, and it was very clear to find that the independent component number 6, which is shown in the middle of these circles, actually has a directed or causal relationship and to other areas, but none of the others is impacting this particular independent component number 6. So we, in this way, and we choose this independent component, and from the ictal data, which is shown on the right bottom, which is showing where the ictal source distribution, that is very well and inconsistent with surgical resection and intracranial recording and the seizure onset zone defined by clinical measure in this particular patient. So that is some of the experimental validation and the work we have done, and our strategy is just certainly this animal model can serve this purpose, but we choose to use a clinical population because in that case we do know that there is a directed information or the causal relationship in epileptic network. So in summary, that the take-home message is that electrophysiological connectome approach, integrating and source imaging granular causality, is a promising approach that seems to merit further investigation. And along this line, as Karl just talk about that, and we could integrate this source imaging with other effective connectivity measure, for example, and DCM or others, and which probably is again pushing this direction and furthermore. And regardless of whatever model we use, the experimental validation will be crucial and to assess any of the non-invasive imaging modality, including the electrophysiological and connectome approach. And a few more technical notion here is that if to push this forward, and one important thing, because electrical source imaging is used to find out from non-invasive EEG or MEG measurement to find out what kind of source information. So keep pushing the source imaging accuracy and specificity remains to be a challenge, and which, although we talk about this complementary nature between fMRI data and electrophysiological information, these two sets of information actually could be integrated together or possibly integrate to do the multimodal imaging and in a reasonable way and to pushing this direction further. Another is that we need more this study on various algorithms to estimate granular causality, not to mention and non-granular causality models such as the DCM. In this particular case, and Laura Astolf in 2007, actually is a very interesting, although some computer simulation results suggest that DTF PDC or DDTF has some difference, but when applied to ERP data in human, and this results show that actually the pattern is quite similar. So there's a lot of work need to be done to find out what a particular algorithm is suitable to estimate the granular causality. And also another issue is how to save the time for most of investigators instead of to reinventing their platform for some of their software, but so there is a free software which is entirely open source that we have developed in collaboration with University of Rome Group and for people to use. And lastly, the message once again is experimental validation is crucial for electrophysiological connectome imaging and like anything else. I would like to take this opportunity to thank a number of people, and including my current and a former student postdoc and various collaborators. And also I would like to thank the NIH and NSF for funding support. Thank you very much. I'm not sure if there's a question. Okay,
yeah, thanks, that was great. So I guess in the end, the aim is to use these without having like a clinical population, right? So the validation is one step, but how would we do this if we don't have sort of the ground truth source? So if we do like a study with a normal population, how can we use this approach?
It's an excellent point. And like, for example, we think about just a functional MRI. When we do the functional MRI in the normal, healthy brain, and we are not going to ask it to say, can we measure local field potential in this particular subject? But we trust our result because functional MRI technology has been established through a variety of validation approach. So in this case, we use epileptic patient, and when we know the ground truth, we know where the seizure come from through the intracranial recording and through surgical resection, that if you resected that node and this patient became seizure-free. And using this approach, we can establish this and electrophysiological and causal imaging or connectome approach. After that, and this approach could be applied to various cases. And that is from technical perspective, but I'm not saying the epileptic network alone would be sufficient. So we would need more. For example, there are some work you could apply TMS and to interact their normal brain network and then to images or connectivity pattern, hopefully, and to validate, or many others too. Yes.
Thank you.
If I may.
Yes, please.
So, I was wondering to what degree frequency band plays a role in this whole analysis. Did you try different... as far as I know, I'm not an EEG person, but as far as I know, EEG works very often on specific frequency bands. I know a bit about Granger causality, that you could apply to the whole time signal or to specific frequency bands. So how does that play a role in this whole analysis? And how does that play a role in the... with respect to one of your first slides where you said fMRI is too slow?
Okay. I guess I was not the person to say fMRI is too slow. We do know fMRI is slow, although it's great. Okay. So to get back to your question, and the Granger causality initial theory is formulated on the time domain. But as I mentioned, Kaminsky in 1991 actually extended the Granger framework to a multivariate autoregressive model, and they propose this directed transfer function, which is in the frequency domain. So based on EEG or MEG analysis, and this is DTF-based, it's essentially is Granger causality, but using DTF or its variant can be applied to a particular frequency rhythm, say like the alpha rhythm, beta rhythm, gamma rhythm, theta rhythm.
So which region is the most important then for these type of analysis?
There is no answer to that question. Okay. So which region is the frequency rhythm is more important is entirely depending on the particular experimental condition and particular brain network. But this approach provides a set of tools to allow you to explore and say you could look at various frequency range and then you say which one does give you the information that you wish.
Thank you.
Last question, please. Thank you.
So to follow up on the first question, when most of the evidence came from epileptic spikes, which are relatively easily localized because they have large SNR and because there are very few sources active at the same time when the spikes occur, and it would be an immensely more difficult task to localize activity in ERPs, for instance, in normal subjects. How do we go about that? I mean, it's the extension from the validation in patients with spikes to the normal EEG responses. We want to look at the connectome for that.
This is an excellent question, and actually I have slightly different view in terms of whether ERP is going to is dissimilar to the spike. And somehow I feel actually ERP is quite similar to spike, even look at the waveform shape. And one of the comments is that in ERP, if you talk about ERP, and if you would talk about single trial, even related response, that is very challenging. But if you talk about ERP, you are able to do the averaging. So after number of trial averaging, the signal-to-noise ratio is improved substantially. And if that information is sufficient to you, and which is reasonably, and to assume that the spike data and could be applied to ERP, actually there was like in Laura's and 2007 paper, and she looked in using computer simulation by changing the SNR, and the conclusion is that if SNR is 3 or greater, actually this approach is applicable, which is a fairly, I think 3 is not that challenging to get in an ERP experimental setting. Okay. All right, so we should move forward, and it's my great pleasure to introduce our next speaker, and Dr. Guido Nolte. And Guido is from University Medical Center Hamburg and has made an important contribution in their imagery coherence and PLI and as applied to connectivity imaging, and he also worked on the forward model on MEG before. Guido? Oh, you're here. Okay. Yeah.
So, Yeah, thank you very much for the invitation. I think this is the biggest hall I've ever been talking in. So this will be a conceptual talk on cross-frequency coupling, so not so many results. Basically, yeah, it's on nonlinear data analysis, but to do that, first of all, I want to say a few words about non-stationarities. So we could look at such data set, for example. So it's a simulation. You see some a time signal, and at some time points it has a value around -3, and then it jumps to values around +3 and jumps back and forth and so on. And when you would show such a signal to scientists, I think almost all would say this is a non-stationary signal. But this is actually wrong. So this was simulated in using just a nonlinear dynamical equation. So in this case, it's a particle subject to a specific force with a double well potential, and sometimes it's on the. I don't have a pointer. I just learned this morning. I don't have a pointer. This really makes it difficult. So sometimes the particle is on the left side, gets little kicks, and eventually the kick is large enough and it jumps on the other side, and so on, and then it jumps back. The key point here, there is no explicit time dependence. So this is stationary. This is what stationary means. There is no explicit time dependence. This jumps just because the force, that's the derivative of the potential, is a third-order function and is not linear. So this is a nonlinear phenomenon in this case. One could look, to study this further, look on how is non-stationarity defined, or what is meant by something is stationary. And this is if statistical moments, for example, say power, a variance, and we calculate the expectation value at some time, and if this is constant, meaning this is independent of time, and if this would be true for all statistical moments, then the time series is considered as stationary. Now we could try this for, say, white noise, stationary white noise, and try to estimate power as a function of time. So, for example, we have a sliding window, measure the variance or square root of variance in that sliding window, and say, this is the variance at that time. So if we do this, we come up with some time-dependent signal. Now this signal, it shows time dependence, but this is fairly irrelevant. The entire process here was stationary. So something, and the whole argument when we say we have a little sliding window, and in that sliding window we try to make some estimate, and then we find this is time dependent. Something must be wrong in the entire argument here. And the point is here, the problem is that we pretend that we can measure a power in a time window. We cannot estimate power in a time window. The only thing we can do, we can calculate an estimator of the power in a time window. An estimator is something very different from power itself. Usually we don't care. We just say, yeah, it's not exact. We know this. But in this context, this distinction is very important. The estimator always depends on time, not because something is not because there's a non-stationarity, but just because we have a finite number of data to estimate it. Therefore, and then we get this time dependence, which doesn't really mean anything. The point is really, if we want conceptually, if we want to have an expectation value at a specific time, an expectation value is an average over an ensemble. We must define at a time an ensemble. And for example, for continuous data, we don't have such an ensemble. So such a quantity like expectation value at a specific time is not defined for spontaneous data. In order to define non-stationarity, we need something like a clock. We need to find at this time This is the ensemble. We could have this, for example, if we have ERPs. Then we have a clock. So I want to demonstrate this a little bit and just calculate something which I would call a linear cross-frequency coupling. So the definition here on the right side, this is like coherence. Now coherence, so X at some frequency F1, X times X star at another frequency F2. This is similar coherence. This is not coherence. In coherence, F1 would always be equal to F2, and there we would have a value X and a value Y. So anyway, but this is a cross-frequency coupling. So if we would calculate something for this like an ERP, say this is a simulation for an ERP. This is clearly a non-stationary case, so we do have a time clock given by the stimulus, and then we would calculate this, what I would call a linear cross-frequency coupling. Then we would come up with the result shown on the right side. You see, it has non-trivial values. Nobody ever does something like that. At least not. Why do we never calculate something like that for spontaneous data? A linear cross-frequency coupling. We don't do this because in order to get something out, we need a clock. This is a non-stationary phenomenon. So let's consider a slightly different case. Say we have the ERP. On the right side, we have many trials, but we just don't know when the stimulus was. So we are just wrong by, say, one trial each. And we do the same calculation again. And then we would observe that the cross-frequency coupling, in this case, would totally vanish across different frequencies. So in this case, linear cross-frequency coupling, linear cross-frequency coupling could not be observed for stationary systems if a clock is not known. In order to see something like that, we would need a clock. But for spontaneous data, there is no such clock, and this gives restrictions on what we can measure. In this case, it would mean if we analyze linear data, the restriction is that we would never observe cross-frequency coupling. And this is a consequence of stationary data. So to my opinion, I would say there's a large misconception around about what non-stationarity actually means. And to my opinion, in 90% of the time when people talk about non-stationarities, they really mean non-linearities. And one could also say, is this just a question of terminology? So I'll give you a few arguments why I don't think so. First of all, there are some technical details for bicoherence. I will show you that below. And then you often hear the argument, you calculate something like, even if you calculate coherence, people would say, well, but in your whole analysis, you assume stationary data. But that's not true. So everything is wrong. I would disagree with that. First of all, if you have, for example, a spontaneous data, you calculate coherence, well, that just is stationary. There's nothing wrong with it. It is nonlinear. But even if it is nonlinear, coherence is a meaningful measure. It's a linear measure, but even for nonlinear systems, you can calculate that like you can calculate power. Also, nonlinear systems have a power. That's a meaningful quantity. The second is that you could there's some risk, if you're not aware of this, is you overinterpret your results. You estimate something, say for spontaneous data, in a sliding window as a function of time, and then you overinterpret your time dependence. This is you just do estimates in time, and then you say, now I see something new. But it's not really new. Everything you see is just a question of variance, just because you have, in each time window, you have a finite number of data. Finally, one should be aware of what the goal is. The goal are dynamical laws. So it is not interesting to know that this brain was in that state at that millisecond. By the time this is published in a paper, it's not in the state anymore. So why would we need that? The question is why and to what are the statistical rules when it jumps? And these are some, if it jumps, say, but these are still some rules. And the rules themselves, they are time independent. And that's what we should find out, not the time itself. Now I want to come to cross-frequency coupling. On the left side here on this slide, I recall some principles of coherence. Say we have two signals, so basically in two trials, essentially, or in two time windows of spontaneous data. Essentially, we observe physically the same thing. So the blue one is a little bit ahead of or the red one, in fact, is a little bit ahead of the blue one. And we observe the same things at two different time windows. And the question would be whether there's a fixed relationship between this blue and the red signal. Apparently, for spontaneous data, the blue and the red always have some phase relative to where your window is, the time window starts. Apparently, and this is really trivial, the phases themselves are meaningless. Well, the only thing what is meaningful is the difference of the phases. And because it is stationary, because we don't have a clock. The clock here is given by a totally arbitrary setting of a window. That's meaningless. And this is all implicitly taken into account when calculating coherence. So I've shown you the definition below. And I mean, this definition of coherence only depends on the average phase difference, not of the phases themselves, which are, of course, trivially meaningless. So if we try to do the same thing for cross-frequency coupling, so here's the most simple version of bicoherence. And this would correspond to 1-2 phase locking. Say we have alpha and the beta range, a slow alpha one, a red one, and a higher beta one. So, and again, in this case, let's assume this is spontaneous data. We set some time windows, but the setting is arbitrary. We always observe physically the same thing. So the only thing what matters is the time difference, say, between the maxima of the red and the blue curve. But what does this mean in terms of phases? For the phases, is not that the phase difference is independent of where the window is set. This is a little bit more complicated because for a given time shift, the higher frequency, the phase propagates faster with time than the lower frequency. So in this case, what would be constant is that 2 times the phase of the alpha would roughly be the same as the phase of the beta in this case. And the question is, it only makes sense to look at this difference and to study whether this difference is more or less constant, and this results to some equation in bicoherence. Like coherence, bicoherence takes this into account. So this was a simple case for one frequency coupled to the double. We can also have this a little bit more general. So bicoherence, a little bit more general, is in fact a function, a coupling, given as a function of 2 frequencies, one frequency f1, another frequency f2, and the coupling really means a coupling in most general form between signals at 3 different frequencies. Actually, it's f1, f2, and the sum. And this is what confuses many people. They say, why is it such a strange way that we couple 2 frequency to the sum of the others? The reason is stationarity. If we have spontaneous data, everything else would vanish as a third-order coupling. So we just look at this quantity because it makes no point in looking at others. People don't like this about bicoherence. They say, oh, but that's not really what we want. We want to have coupling between 2 different frequencies, not between 3. I will come to that for phase amplitude coupling later. But first of all, I'll show you a few results on what you would typically get. So this is typically one channel, bicoherence as a function of 2 frequencies. And what you can see in almost all subjects very clearly, are these peak, for example, at 10 hertz. 10 hertz would mean coupling between 10 and 20. 10-20 would mean coupling between 10, 20, and 30. So you can say all these higher, this is alpha and all these higher harmonics. And this is really where the title of this talk comes from. It says, well, we study alpha rhythm all the time and look at power. So, but these nonlinear effects, they are so strong in typical EEG, MEG data. They contain so much information. These are actually complex numbers. I'll just show you the absolute value. We can study them also. They reflect valid nonlinear properties of alpha. So contained in the higher harmonics. And usually, when people talk about cross-frequency coupling, they say, you must make sure it's not a higher harmonic. Why not? Higher harmonics reflect a nonlinear property of alpha. So it's a valid thing to study in this case. Actually, this is for univariate data. In coherence, you would never look at univariate data. It makes no sense. But for bicoherence, you can do this univariate and multivariate. So this is other examples of what you would typically get. This is would be a hard artifact, so you must be careful. If you see something like this looks like, oh, great, but it's really just an artifact. So this would look like a muscle artifact. You also get a signal, but not very interesting. Here you see some other thing which I do not know. Very weird. You can see this in around 20% of subject. I don't even know what this is. Probably, I would guess it's some muscle artifact. So I would say 80% it's muscle artifact. I'm pretty sure it's not a technical artifact. You can also distribute this over the whole head, and you would see the signal occurring here, in this case, in many sensors, but often only in very few. Now, let me come to phase amplitude coupling. So this is a simulation, typical simulation, theta gamma coupling. So we have a slow wave, theta, and when the phase of the slow wave, when the theta has a maximum somewhere, then we have high gamma power. This is a classical case of phase amplitude coupling. We can have them separately as two signals, but we can also add them up, have a univariate signal, and then we would look like a picture on the right. To recall the principles of phase amplitude coupling, first of all, if we write down just the theta phases, this is what I show you is just one sliding window. We do this for the entire data set, write down all the phases. It would look like this picture on the left, on the lower left. Just the phases of that is just arbitrary, just random. However, if we weight the phases with the power of gamma, then we would say always when the phase is near zero, the gamma, the power is very, very large, and when the phase is on the other side, the power is very small. So phase and amplitude are coupled. And this is expressed in the quantity for phase amplitude coupling. It's just a weighted average of the phases. So in fact, also this in principle, phase amplitude coupling PAC is a function of two frequencies, and we can just calculate that. We can also calculate bicoherence and just look what comes out. So here I just show you both are fairly similar. So bicoherence and PAC, at least for this case, there doesn't seem to be a big difference. Here bicoherence is symmetric and PAC is not, but this is just by construction. You can also bicoherence set the lower triangle to 0. But there's one weird thing which confused me for some time originally. So if I write again down the formula for PAC, and if I make a little change here, so I have the phase of the slower wave, say theta, and rather than the phase, I also weight the phase with the amplitude of theta. Shouldn't make a big difference, and it doesn't really make a big difference. And if I do this, I come up with this formula and compare this with bicoherence on the right side, and probably it's too quick to go through formulas, but in this case, so I tell you, it's almost exactly the same thing. PAC and bicoherence are almost the same, except that if you really look at it, PAC, in this form at least, should be 0. because, and that's for spontaneous data. Spontaneous data are stationary. And non-stationary effects, you must have a particular relation between the frequencies. You have F1, F2, and the sum. But for Puck, you don't have it. You just have two frequencies. So why is it then not zero? So that's the question. Why doesn't Puck vanish for stationary data? So one can go through the mass. The solution to is that for Puck, it's calculated in a fairly complicated way. So basically, it's especially for the high frequency, you must use a filter which is not narrow band. So you say, oh, this is gamma at, say, 40 hertz. But your gamma is, it's not really at 40 hertz. You have to filter it before you apply a Hilbert transform, say, between 30 and 50 or something. You have to use a very wide band noise. If you make a narrow wide band filter, if you make a narrow filter, it would vanish. So basically, what you think is a relation between two frequencies is really a relation between all frequencies, so for gamma, in a range. And you need that range to come up with a non-vanishing result. So actually, if you go through the mass, you will find pretty much, this was with the modification, but that phase amplitude coupling, you can express, this is just a smeared version of bicoherence. So in this case, then I would advocate, well, then why don't you just calculate bicoherence in the first place? Then at least you can see whether there are strong peaks or it's just a smeared version of it. So this was all conceptual part. I'm coming to the end now. I'll show you a few examples for this. So in this case, we studied schizophrenics versus control. The results are a bit preliminary. So we can do this. Look at phases for normals, look at phases of bicoherence peaks for schizophrenics, and then we can see, is there a difference between, a systematic difference between normals and patients? And there are. I wrote you some p-values for that at the various peaks. The others are fairly irrelevant. And also when you look at that, here, this is a picture of two phases. Phases for controls are blue, phases for patients are red. So I show you two phases. And then you can also see they pretty much have different phases. And to do something like that for power values, also coherence, would be very difficult. It would be very difficult to see a difference. So these nonlinear results have contain very rich information and contain a large potential to separate, for example, controls for patients. Here is, and this is my only slide on, everything so far was univariate, but this is now, but it doesn't really matter. You can also do it in a multivariate way, done basically by Federico Keller from Chieti. And I show you here phase differences of, and I can't go to the details here, of a variant of cross bispectra which is robust to artifacts of volume conduction. And you can calculate phase differences between two sources, and then you would see, look at that difference, and then you can see across many subjects that there's a pretty stable phase difference. And I want to point this out because I think usually it's extremely difficult to observe anything which is stable across subjects. So most of the time you find enormous variation of anything you calculate across subjects. Okay, that was it. So my summary, I would say, so this is to hint on what I would think is a misconception. Spontaneous brain activity is nonlinear. It is not non-stationary. Spontaneous activity is stationary. Then the second is phase amplitude coupling is essentially a smeared version of bicoherence, I would say. And I would say what could be used bicoherence for, and most of all, it's just empirically what comes out in the data, that it gives new opportunities to study the alpha rhythm. Most of all, I showed univariate cases, but you can also do it in a multivariate way. Okay, thank you. And thanks to some people And I only mention Laura Mazzetti because on this list she's the only one here. And the others are punished. So thank you.
We have time for one possible question. Yes, please.
Okay. Fantastic presentation. For what it's worth, you get my award for the best presentation at HBM.
Oh, thank you.
I would encourage you to put your opening slide on your webpage. I was at the time-varying functional connectivity session a couple of days ago and felt like weeping because there wasn't a speaker who was not confused about the difference between time-varying, stationarity, and another word, dynamics. And I'll ask you a question about that in a moment. I just want to add my comments about your beautiful explanation of the relationship between the bicoherence and the phase amplitude. Because I think with this nonlinear stuff, the phase amplitude is the one that's very easy to convince people that it's worth looking at. The bicoherence is far less obvious a quantity. But my question is this, a leading question to give you an opportunity to explain to people the difference between non-stationarity, time-varying, and dynamics.
Oh, that was a difficult question. I should, but yeah, I'm not exactly sure. By dynamics, I just mean a specific dynamical law, which is, and by time dependence, I mean any knowledge like an input which you give and which gives in a very in a meaningful way a time clock. A time clock could be anything like a stimulus, for example, anything which is spontaneous. As soon as you don't have a clock, you must consider this as spontaneous. I'm not sure if this is a good answer to your question. People sometimes would say, yeah, but perhaps it is non-stationary, but it's just that you don't know the non-stationary effect. But if you don't know it, there's no point in even speaking about it. Then you must, non-stationary means you must have a clock relative to which you can analyze data. And if you don't have such a clock, it's not available. So you must really consider it as stationary. Stationary it's not any time dependence, any principal time dependence is not available to me to study.
Okay, thank you very much. And because the